In the fascinating world of chemistry, we're looking at collision theory and later into energy of activation. Collision theory says the more collisions occur, the more rapid or kinetic the reaction proceeds. So, Arrhenius first came up with the concept of collision theory where K is our rate constant, A is the number of collisions that take place, E sub A is the energy of activation, R is a constant, and T is the temperature in Kelvin. Problem we have is the number of collisions is difficult to measure sometimes, so there had to be a way of getting rid of it. So what Arrhenius decided to do was subtract two different reaction rates at two different temperatures. When he did that, he found that he could divide out negative E sub A over R, and then because of that, both of the ln of A's will subtract away. He didn't like the negative E sub A though, so he flipped it. When he did, he had to flip the temperatures around. And so we get a final Arrhenius equation of the natural log of K sub 1 over K sub 2 is equal to the E sub A energy of activation over our constant, all divided by, all multiplied by the 1 over the temperature 2 minus 1 over temperature 1. So again, K sub 1 is the reaction rate at temperature 1. K sub 2 is the reaction rate at temperature 2. E sub A is the energy of activation. Our constant is 8.31 joules per mole Kelvin. T1 is a temperature 1, and T2 is temperature 2. So let's look at a problem. Calculate the energy of activation if reaction rate triples as the temperature goes from 30.27 degrees Celsius to 77.24 degrees Celsius. Now, when we take the K1 over K2, it's going to end up being 1/3, not 3. The reason is because we're going from the lower temperature to the higher temperature. The higher temperature is going to, the lower temperature, the constant for the higher one, the lower one's on the bottom, and the temperature of the higher one is on the bottom. So we end up with 1/3 when E sub A is unknown, R of 8.314 joules per mole Kelvin, and temperature 1 is 30.27 degrees Celsius, and T2 is 77.24. Now, I don't really like that fraction. I much prefer to have it a whole number. So the way that I do that is I flip my temperatures. If I flip my temperatures around, making T2 the lower temperature and T1 the higher temperature, I can get a whole value. Of course, these have to be in Kelvin, so we add 273 and convert my units to Kelvin. So we take our equation, the Arrhenius equation, ln of K1 over K2 is equal to E sub A over R times 1 over T2 over 1 over T1. And I'm solving for E sub A, so that's going to be ln of K1 over K2 times R, all divided by 1 over T2 minus 1 over T1. Put our values in, ln of 3 times 8.314 joules per mole Kelvin, and then we're going to divide that by 1 over 303.27 Kelvin minus 1 over 350.24 Kelvin. When we divide that through, our Kelvins will all cross out. We get 20,655 joules per mole, but most energy activation is in kilojoules per mole, so we're going to have to convert it to kilojoules per mole, so my joules cross out. I get an answer of 20.655 kilojoules per mole, and that's my answer. Second problem we'll do in class, find the temperature needed to increase the rate of reaction by 5 times if the reaction is initially at 19.655 degrees Celsius and the energy of activation is 43.164 kilojoules per mole. That's it for class. Take care and be good.